Welcome back to the deep dive. Today, we're doing something a little different. We're not just talking about what these huge language models can do.
No, today we're going straight to the source.
We are going deep into the engine room. We're looking at a single, super optimized function that is really at the computational heart of a model like Llama 4.
And we actually have what looks like a genuine code snippet to work from. It's from a file named MoE.py, so a mixture of experts layer file. This is a pretty rare look under the hood.
It really is. The function is called batched SwiGLU, and we have to give a shout out to Piotr Skorik for detailing this. So, for you listening right now, our mission is pretty simple. We want to help you understand two key concepts that let Llama 4 scale up to trillions of parameters, MoE and SwiGLU. And then we'll see how that word batched is really the key to modern GPU efficiency.
Exactly. This one function, it's like the core building block for what they call a single expert. If you understand how this works, you pretty much understand how Llama 4 can be so massive, but still so fast.
Okay, let's start with the big picture then, the strategy. Mixture of experts, or MoE. We hear this term all the time now. So why is it so essential? Why does Llama 4 need experts?
It really comes down to economics and physics. It's that simple.
Okay.
When you get to 1 trillion parameters, you just can't afford to activate every single part of the model for every single word you process. A traditional dense transformer at that scale, well, the compute cost would be astronomical.
You literally melt the servers.
You would. So MoE is the architectural answer to that problem. Instead of one giant dense network, you have, well, maybe hundreds or thousands of smaller specialized subnetworks. The experts.
Right. And the core principle that makes it all work is sparsity.
Sparsity, that's the word. So when a token comes in, let's say it's a really obscure medical term or a piece of code, a router basically steps in and asks, okay, which of my specialists here is the best fit for this job?
And what's the actual payoff there, computationally?
It's just massive. I mean, the source material we have confirms what we've seen in other MoE models. For any given token, you're only activating a tiny fraction of the total experts.
How tiny are we talking?
Typically, maybe 2 to 8 experts get used out of hundreds or even thousands.
Wow. Okay, so let's put that in perspective. If you have, maybe 1,024 experts total and you only use 8 of them, that's like a 99% reduction in the active parameters for that one computation.
Yeah, exactly. So the model can have this enormous total capacity, trillions of parameters, but the active computational footprint for any single task is actually incredibly small.
It completely changes the scaling game.
It does. So MoE decides which parameters to use. But then once you pick your 2 to 8 experts, they have to do something really effective. And that's where SwiGLU comes in.
Perfect transition. So section 2. SwiGLU, the switch-gated linear unit. We see this all over the place now, replacing the older ReLU-based MLPs. Why? What makes it so much better?
It's all about expressiveness and control. ReLU, the rectified linear unit, is very simple. It's basically an on-off switch. If the input is positive, it goes through. If it's negative, it's 0.
Right, a hard cutoff. But SwiGLU is different. It's a gated activation function.
It is. Think of it less like a switch and more like a selective volume knob.
Okay, I like that. Tell me more about this gate.
So SwiGLU takes its input and kind of splits it into 2 paths. One path becomes the gate, and it runs through a function called SciLU, the sigmoid linear unit. You'll also hear it called swish.
And SciLU is smooth, right? No sharp corners like ReLU. That seems important for training.
Absolutely. That smoothness lets the model learn much more nuanced relationships in the data. So the output of that gate is then multiplied element by element with the second path, the value projection.
So it modulates it. It controls exactly how much of the value gets to pass through.
Precisely. It's a much more dynamic process.
And our source material notes that SwiGLU is parameter efficient because it shares parameters between that gate and the value projection. But hang on, that seems a little counterintuitive. If these experts are supposed to be specialized, doesn't sharing parameters limit that specialization?
That is a really great question. And you're right, you are trading a tiny bit of, let's say, independent capacity. But the gain in overall efficiency is huge.
Okay.
And because SwiGLU is so much more expressive than ReLU, that shared structure can still learn incredibly complex things. Plus, and this is key, the actual weight matrices, the W1, W3, W2 we'll get to, they are not shared between experts. Each expert has its own unique set of weights.
Got it. So the computational pattern is efficient, but the learned knowledge inside the weights is totally unique to that expert. One expert's SwiGLU can be tuned for, say, legal documents, and another one for Python code.
Exactly right. And that brings us perfectly to the name of the function itself, batched SwiGLU. because that specialized engine has to be just ruthlessly fast.
Right. And now we get to the heart of what makes GPUs so powerful. The batched part. For anyone listening who knows LLMs but isn't, a deep learning engineer, why does adding batch to a function name scream high efficiency?
It's all about how GPUs are built. They're parallel processing machines. They can do thousands of things at once. What they hate is doing one thing at a time, like in a Python loop.
So batched means you're not feeding it one piece of data. You're giving it a giant block, a tensor, and telling it to process everything at the same time.
A giant three-dimensional block, yes. The shape is usually something like batch size, sequence length, hiddendom.
Can you give us a quick metaphor for what those dimensions mean?
Sure. Let's say you have 32 different users sending prompts at the same time. That's your batch size.
Okay, 32.
And maybe each prompt is 2,048 words long. That's your sequence length. And the hiddendom, say 4,096, is like the internal bandwidth, the width of the pipe that processes each of those words.
So you're pushing 32 different long documents through 4,096 parallel channels all at once.
You are. And to do that, the code uses torch.bmm.
Which stands for batched matrix multiplication.
It's the command that tells the GPU, hey, I have this whole stack of matrices, multiply them all simultaneously. It's orders of magnitude faster than any other way of doing it. Absolutely essential for low latency.
And another efficiency trick here, which is very Llama-like, is that this code doesn't use bias terms. Why leave those out? Isn't that just a simple addition?
It is a simple addition, but at this scale, every single operation costs something. Bias terms can help a bit in smaller networks, but in a massive model like Llama 4, two things are true. First, the model is so big, the weights can usually learn to compensate for any missing bias. And second, skipping that addition across trillions of parameters actually adds up to a noticeable saving in memory access and computation time. It's a speed optimization, plain and simple.
No bias, total parallelism.
Okay.
Yeah, so let's define the inputs for this machine. We have X, the input data, and then 3 weight matrices, W1, W3, and W2.
Right, and these weights are where the expert's knowledge is stored. The Llama naming is a little confusing, so let's clarify it.
Please do.
W1 is the weight for the gate projection. W3 is the weight for the value projection. They both take the input and project it up to a larger intermediate size. You can think of them as the up projection weights.
So if our pipes with the hidden dimension is 4,096, this intermediate size would be much larger.
Yeah, typically about 2.5 to 3 times larger. Let's say it's 11,008. So W1 and W3 are these big matrices that expand the representation from 4,096 dimensions to 11,008.
That's where the complex analysis happens.
That's the space, yeah. And then W2 is the down projection weight. It takes that expanded 11,008 dimension representation and squeezes it back down to the original 4,096.
All right, we have the ingredients, we have the motivation. Let's look at the actual calculation. The very first line of the function does almost all the work. Middle out GF, SwiGLU, torch.bmx, W1, torch.bmmx, W3.
This is SwiGLU in action. You're basically running two parallel computations on the same input, X.
Let's take the first part, the gate. That's SwiGLU, torch.bmx, W1.
So you do a batched matrix multiply with a W1 gate weight, and then you immediately apply that smooth SwiGLU activation function. The result is your filter. It's the tensor that decides what's important.
And the second part is the value, torch.bmmx, W3. Just a straight projection using the W3 weight.
Exactly. And both of these tensors now have that bigger intermediate shape, batch, sequence, 11,008. Then comes the most important part, the little asterisk, the PA between them.
The element-wise multiplication, this is the actual gating.
This is the gating. The filter tensor, which has all those values between 0 and 1 from the SwiGLU function, is multiplied against the value tensor.
So it's like it's saying, okay, dimension 500, you're not very relevant. You only get 10% of your signal through. But you, dimension 8,000, you are critical for this token, you get 95%. A dynamic filter across thousands of dimensions.
That is a perfect way to put it.
Yeah.
And the result of that is middle out of GEF. It's our fully transformed, gated, but still very large intermediate representation.
So now I just need to shrink it back down. That's the final line of code. Return torch.bmm, middle out GF, W2.
The down projection. You take that big intermediate tensor and hit it with another fast batched matrix multiplication, this time using the W2 weight.
And that takes it from 11,008 dimensions all the way back down to the original 4,096.
It does. The output tensor now has the exact same shape as the input X. It's been fully processed by the expert, and it's ready to be combined with the outputs from the other active experts.
It's so elegant when you see it like that. You explode the data into a huge space for complex analysis, apply this incredibly expressive gated filter, and then compress it right back down, all in 2 lines of highly optimized code.
And that tiny function, batched SwiGLU, repeated over and over, is really the engine of Llama 4. It tells you everything about their design priorities. Expressiveness from SwiGLU gating, specialization from MoE, and raw speed from batched GPU ops.
So, to bring it all together for you, the learner, when you think about how Llama 4 achieves its incredible scale, just remember this one function. It's the core transformation inside every single specialist in the model, combining the best of modern neural network design with the raw power needed to run a system with trillions of parameters.
And it's important to remember the context, too. The output from this function is just one expert's opinion. The MoE router then takes the outputs from all the active experts and blends them together, usually with a weighted sum, to create the final representation for that token.
This is where it gets really fascinating, though, and makes you think about what's next. This whole implementation shows a very clear design choice. We're moving away from simple, one-size-fits-all operations like ReLU and toward these very sophisticated, gated and batched functions like SwiGLU, built from the ground up for speed and sparsity.
It's like model designers are now treating every single floating point operation as a precious resource.
So the provocative thought we want to leave you with is this. If this much customization and optimization goes into just one function, just for transforming data inside a single expert, what else is in there?
Right.
Imagine how many other specialized, highly tuned functions must be hidden across Llama 4's trillions of parameters, each one probably surgically designed to use SwiGLU for complex learning and batched ops for speed, all working together to make the whole thing feel instant.
The complexity of the optimization is now scaling just as fast as the models themselves.
We'll leave you with that. Thanks for joining us on the Deep Dive.